Hey, what's up, Mr. Ends? It's Juby.
And it's Emma.
Now, if you've ever bought helium-filled balloons for a party, you'll notice that they behave differently from a regular balloon that we fill with the air from our lungs, obviously. Now, that may be obvious to you, but do you know the true physics behind it? You probably do, because you're a physics teacher! Please give us a good grade. Anyways, that's what we're here to talk about today. Ruby and Elmo's Physics Project!
Air is composed of a variety of elements, but it's predominantly made up of nitrogen. A certain amount of atoms of nitrogen will take up approximately the same amount of space as an equal amount of helium atoms. The difference is that the mass of the helium atoms will be significantly lighter than the mass of the nitrogen atoms. This demonstrates a discrepancy of densities, which is the reason that helium floats upward in the air.
Now, when we're talking about helium balloons, as long as the sum of the masses of the helium, the balloons, and the string is lighter than the mass of the air displaced by the balloon, then the balloon will float.
The reason this is happening is because of buoyancy forces. These forces act on an object when it is surrounded by a gas or submerged in a liquid. The force of buoyancy is equal to the force acting on the bottom of the object minus the force acting on the top. To calculate those forces, you need to find the pressure on the top and bottom of the object and multiply each by the area to which they apply. To simplify, pressure is equal to the product of the density of the fluid times gravity times the height of the object. By doing simple math, we can rearrange this formula. So we find that the distance cubed, which is the volume, times density times gravity is equal to the force of buoyancy. So the volume times the density is of course equal to the mass, meaning that the mass of the fluid displaced times gravity is the force of buoyancy, which is of course the weight of the fluid displaced.
So for our equipment, we had a 250 gram house, a scale to measure the change in masses as we added balloons. We didn't use this one, but it was similar. We needed 40 helium balloons, a tape measure to measure the circumference of the balloons, and a device that took videos and was equipped with iMovie.
Now, this is all very interesting, but we wanted to see buoyancy in action, so we created a sort of analytic experiment. Disney's movie Up is renowned for its plot about an old man trying to lift a house off the ground with just helium balloons. Any person with an understanding of physics can see this is illogical for so few balloons to lift an entire house. Fake. 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 Fake.
Equipped with the knowledge of some wrong being committed, Juby and I, we were inspired to discover how many balloons it would actually take to lift a house the size of Carl Fredrickssen's in the popular movie.
Yeah, we're Disney Mythbusters.
Since we're both broke teenagers and unable to afford an actual house, nor the amount of balloons to lift it, we settled with a little wooden house that Emma found at the dollar store. For aesthetic purposes, Sam, Emma's sister, painted it to resemble Carl Fredrickssen's house. Then, on a lovely rainy Wednesday, we went to the dollar store and bought 2 10-packs of yellow balloons. If you choose to recreate this experiment, we'd recommend choosing a color that isn't yellow, since you'll draw too much negative attention to yourself.
In any case, as we watched the poor Thrifty Foods lady fill up like 5 balloons, we realized that 20 balloons was not enough to lift our 250 gram house. That said, we had already spent like $20 on balloons, but ultimately decided that Mr. Enz's physics class was worth it. We walked back into the dollar store and bought 10 more yellow balloons, and then we asked the Thrifty Foods lady to fill 7 more.
We walked back home with our 27 helium balloons and panicked as they started to sag. later, we realized that this was due to the rain, and we allowed them to fully dry before proceeding with our experiment. In addition, our house, predictably, wasn't exactly 250 grams, but luckily this was a pretty easy fix.
Okay, so here we have our house. It's about 230 grams, as you can see on the scale. And we want it to be exactly 250 grams, so what we're going to do is we're going to use my house key. I'm going to stick it in there. And since that's only 249, we're going to stick an old piece of bread in it because that's about 1 gram. And here you have DIY 250. Nice.
After the very scientific process of changing the mass of the house, we went outside and added 1 balloon at a time. This did not take a long time, and it was not frustrating at all.
10 balloons later.
11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28.
Apparently, the gods hate us because we ran out of balloons. And the house stayed planted. Fortunately, around that time, Juby's neighbor Derek walked out and he saw the mess we were, and he decided to give us a ride to Country Grocer to get more balloons. Though we were tempted to just chop off a bit of the house so we would have to use less balloons, we decided against it because 1, in the name of physics, and 2, because it messed with our calculations.
So, we added other balloons but didn't really film it because Derek was there and he already thinks we're weird. It took about 34, 35 balloons for it to skid and 36 balloons to completely lift it. 36 balloons. I think it's the water. Yay! The next step was to find the volume of the balloons. We did this with 2 methods. The first one was the water displacement method, which was when we fully submerged a balloon in a bucket of water and saw how much water spilled out of the bucket, see how much it displaced. It won't go any further. The second method was by compressing the balloon into what we thought looked like a sphere and finding the circumference and doing the math based on that, much like this. We don't have a clip of it because at that point we were too embarrassed. Anyways, during this process, we realized that the water method contained a lot of errors and that the water could have been given to people who were actually thirsty instead of, submerging a full balloon into it.
The next thing to do was to find the weight of the average balloon could hold. We did so by putting the house on a scale and adding a balloon to it, then subtracting the different masses. By using this method, we found that the average dollar store balloon could hold about 7 grams, and the average Country Grocer balloon supported about 10.6 grams, about half of what we hypothesized. This entire process took from 3:30 p.m. to 12 a.m. We did it in one night because, like us, balloons have lifespans, and the calculations had to be made before they lost too much helium. The next morning at 7:30, we calculated the mass that the balloons could hold and concluded that they held significantly less after only 12 hours. This means that Carl would have had to travel all the way from Oakland, California to Bolivar, Venezuela, which is approximately 6,959 kilometers, really, really quickly if he hoped to make it to his destination before his house sunk too far down. The next step in our experiment was to see how all of this information connected with an actual house.
So, looking at our calculations, what does that tell us about the house from the movie? Apparently, the animators drew over 20,000 balloons for the liftoff scene, and they drew 10,000 for the other floating scenes. I imagine they were a little tired of drawing balloons after the 10,000th one, but the laziness gave birth to an inaccuracy that teaches kids incorrect physics. No way could an 1,800 square foot house be lifted by so few balloons.
According to our calculations, the force of gravity on our experimental house was 2.45 newtons. Although we did use 2 different types of balloons, the house was mainly pulled by the yellow dollar store ones. Using the average change in mass each balloon created, we were able to calculate the average net buoyancy force per balloon. So we used two methods to find the number of balloons necessary to lift Carl's house. For the first method, we went according to masses. So we took the 0.144 balloons per gram figure that we found, and we multiplied that by the mass of Carl's house. This gave us a number of 32,332,032 balloons. Now for the second method, we went according to the force of buoyancy. So we took the force of gravity of Carl's house and we divided it by the force of buoyancy per balloon. This gave us a number of 31,889,484 balloons.
All the calculations just performed were done using the force of buoyancy derived from the experiment. If we recalculate using a slightly more mathematical path, we discover that the force of buoyancy is equal to 0.116 newtons.
This gives us a new number of balloons equal to about 18,968,745 of these bad boys. Although this equation was one that looked much fancier, it relied a lot less on our experiment.
One website informed us that the technicians at Pixar estimated Carl's house would need about 23.5 million balloons, so we're using that as a reference point. Here we're calculating the mass of Mr. Fredrickson's house. The Disney creator said that his house was 1,800 square feet, so we're rolling with that. A general rule of thumb for construction is that it's 275 pounds per square foot for a two-story house. This gives us the whopping mass of 495,000 pounds. And since we want this in kilograms, so it's easier to calculate, we get about 200,000 kilograms. In grams, that's about 200 million. So, based off our experiment, we found that it takes 0.144 balloons for a gram. So, that means that we need about 3.233 times 10 to the 7 balloons. That's a lot. Now, let's say you try and lift an actual 200,000 kilogram house and also manage to afford 32 million balloons. Despite this, you would not float. Why? Because there's a bunch of different factors that we didn't cover. The math we did only covers Mr. Fredrickson's house and not the foundation or the furniture or Mr. Fredrickson himself. So, in order to be as accurate as possible, we decided to calculate these additional masses.
Let's start with the furniture. If we add up all the masses of the average furniture pieces found in a single elderly man's home, it would calculate out to be about 1,225 kilograms. In newtons, that's about 12,000.
Next up is Carl Fredrickson. An elderly man his size would be about 90 kilograms, meaning he'd weigh 880 newtons. So now that we've covered the furniture and Carl, let's talk about the foundation. If Carl's house is 1,800 square feet, we only need about 900 square feet to work with, since we only need the area of the bottom of the house. A site told us that the minimum thickness for a foundation is 12 inches. So that means the total volume of this foundation would be 900 cubic feet. Since it's 68 kilograms for 1 cubic foot of concrete, that would give us 61,200 kilograms, which in grams would be 61,200,000 grams. This gives us a total of over 8 million balloons.
So if we incorporate these last three things, the furniture, Mr. Fredrickson, and the foundation, we find that we need an additional 9 million balloons. Adding this to our previous figure of 32 million, Mr. Fredrickson's house needs a total of 41 million balloons just to be lifted off the ground.
So our original hypothesis was as follows. If the average balloon can lift 14 grams, then it'll take about 18 balloons to lift a 250 gram house. This hypothesis was wrong, though, for multiple reasons. First, the 14 gram figure was found online, and it referred to a slightly bigger balloon than the party balloons that we used. In reality, an average balloon should hold about 10 grams, changing our hypothesis to 25 balloons. In any case, this is still wrong. The reason is because it doesn't account for the mass of the string or the balloon itself. So in our measurements, we found that the average yellow balloon only held 7 grams.
Along with the errors in our hypothesis, we also had a bunch of mistakes in our experiment as well. For one thing, we didn't take into account the mass of the furniture, nor the wind that could have messed with the experiments. Also, since it took a while for us to complete this experiment, our balloons started losing helium, which would have affected how many could have lifted the house. Since we didn't buy enough balloons the first time, we also had to get some more from a place closer to our house, meaning they weren't the same brand. The difference in volume between the white and yellow balloon could have had an effect on the results. The weather was also a big factor to this experiment, and since it was raining during the time of our experiment, the water droplets probably weighed the balloons down, which, now come to think of it, is unrealistic in the movie, since you can see it's like pouring down rain and the house doesn't sink at all. There were also quite a few mistakes in the way we measured the volume of the balloon. First of all, the water method probably didn't work very well, and since we had to squish the balloons to find the circumference, it was all approximate, and our squishing was probably not precise at all.
During our experiment, the mass of the house fluctuated within a 2-gram range. This may have minorly affected our calculations.
Really, a problem is that we're just broke, struggling high school students, so we couldn't afford to buy 40 more balloons to try the experiment again in better conditions and trying out different variables.
So throughout our calculations, we made a few assumptions. First, that no balloons burst from contact with another object, and second, that the changing air pressure and density due to altitude were negligible. A few more things wrong with the movie were that not enough balloons popped or sunk in the storm. Also, the tarp that Mr. Fredrickson used to cover his balloons before liftoff could not possibly have been heavy enough to keep all of the balloons down. Lastly, we assumed a straight trajectory, so we didn't account for the wind blowing him off course.
Where did I go wrong? I lost a friend somewhere along in the bitterness. No, Jimmy!